Hello everyone, in this video we are going to implement RLHF in JAX using PPO. And as stated in last video, first I'm going to start off with a diagram. I'm going to draw out exactly what we're building so we can have an overview and a good understanding of what we're building before we actually go into the code. So if you guys just want to jump straight into the code, you guys can jump to whatever timestamp the code is at. But right now I'm just going to draw a diagram and we're going to see how RLHF actually works. So let me share my screen. You're going to see that RLHF obviously has a lot of parallels with PPO. And so it's not an entirely new concept. What it is a different way of going about the concepts that we already know. Obviously, we've already built PPO, so that's not something new. But what's new is having to deal with two additional models, which are the reward and the reference model. Also different things like the KL penalty. Let me outline these. This is the same drawing from last video, right? We've dealt with this little box right there, that little blue box. But with this purple box, having a reward model and having this reference model that we perform a KL penalty on per token, there things can get a little weird and a little different. So first, I want to actually outline what the whole process is like. As you know, PPO has two steps. PPO in general has two steps. We have the rollout where we collect the data as it's an online RL training method. So the rollout, here we collect data. And then we have the actual updates. We do these updates for PPO epochs, if you guys remember that, which is normally like around 3 to 4, around there. I'm going to focus primarily on how we collect the data because updating it is just model updates and all that. But yeah, so another overview of what RLHF is. Well, the three steps of this post-training pipeline that all these papers went over. We have step 1, which is supervised fine-tuning. We're not really focusing that in this video, but supervised fine-tuning, you just fine-tune the model and further train your pre-trained base on a data set of question-answer pairs or question-reasoning-answer pairs. The answers are written by a human, which are what that person, probably an expert or something, deems to be the most perfect and aligned answer that would be possible. And that way we kind of train our model to, instead of just predicting next token, it can answer questions. From there, we have our step 2, which we train a reward model. Now, this part is going to be important for us. We're actually going to implement this ourselves today. We train a reward model to basically be able to score a prompt X and give a reward for an answer for a prompt and answer pair. The reward basically signifies, it's a scalar value that signifies how good that response was. Obviously, the whole point of this is we want a model to do this. We don't want a person to do this. So what we do is collect a bunch of X, Y pairs through what we talk about. We're given a prompt, you get different responses, and then you choose a winner and a loser. So we create a data set of that, and then we train our reward model using the Bradley-Terry loss function, which was, we have our loss, and it's this log probability of the sigmoid of the reward of the winner minus the reward of the loser. And what we want to do is get this as separated as possible so that we get a low log. And so our job is minimizing this loss function. Again, we're going to implement this later on in this video. So now once we have a fully trained reward model, what we do is we use PPO. So step 3 is the actual policy training, PPO in this case, where we have our actual model, we feed it a prompt, we feed it an answer, or we feed it a prompt, it outputs an answer Y, then we pass it through the reward model, this pairing, so that this outputs a reward, and then whatever this reward is, high, low, or in our case, since we normalize it, positive or negative, we want it to be as positive as possible. We use this reward to train this model. And then we do another passing, and in theory, our policy, which is the king model that we want to train, improves in every iteration. And so we know that in PPO, in general, we have, like I spoke of up here, we have our policy or our actor that generates, that outputs a probability distribution to an action space. And then we have our value that basically, given our state, it kind of grades the state that we're in. And we use this to be able to calculate, well, so the value outputs a value. We use this value to be able to calculate an advantage. And this advantage basically tells us if we're doing better than average or worse than average. The importance of this is this kind of serves as our return in a way. It basically tells us how good each step is along the way. It's very similar to how in Reinforce, which we spoke of at the beginning of the series. In Reinforce, we generate this return that is calculated off the final reward, and we kind of just propagate backwards through each step, and we give a discounted reward. Again, remember, the problem with that is that we are giving too much reward and too much credit to, let's say in step 3, we did a certain action. Just because we did that action doesn't mean that that was the best action for that state, even though our reward at the end could be a high reward. So what advantages do and what a value does is it grades each step so that we don't assign too much credit or blindly assign credit, but we have a model that actually approximates a credit for a given step, if that makes sense. And so in PPO, we train these two simultaneously. Now, the difference with using PPO for a language model or for language modeling post-training is that, let me write policy here again and our value, is that in our environment, we don't have something that explicitly gives us the reward. So now that's the whole point of this reward model. We have the reward model that now outputs an actual reward. And then, as you know, we have a KL penalty that we have to calculate per token, which basically diminishes which basically alters the reward for that specific step depending on how far the policy got from the reference. Now, the reference is copied from the original policy before any training is done, and it kind of and the reference basically signifies our model before we did all this reinforcement learning stuff to it. This model is basically our supervised fine-tuned base. Basically, whatever we trained the policy, whatever this outputted as the policy or as our LLM, this is what we use as our reference point, because this has verifiably good ability to output a response given an answer and to have good text generation, basically. What we find in studies is that the policy can begin reward hacking and outputting behaviors that would give a good reward, which is, again, why we need a really good reward model in the first place. But this starts kind of cheating that system, and maybe it even gets to a point where it's not even generating text, but it's generating something that produces a good reward. And so just because we have a good reward, that doesn't mean we have the best policy possible in that instance, because now our trained policy just outputs gibberish that gives a good reward, but isn't good, as a human reads it. And that's why we need our reference. We don't want this to stray too much. And so we have a ratio. If you guys remember, it's like the policy. Then we have the reference here. We have this ratio. We multiply times a beta hyperparameter. And so we find the KL divergence of that. And that's what we have right here. And so that leaves us with, in memory, having 4 models. 2 frozen. Frozen ones are going to get an icy blue. These 2 are frozen, right? Because this reward was already trained in a previous step, which was this step 2. And then we have our reference. It doesn't get updated. There's no gradients that pass through it. That we want to stay firmly as our step 1 model. So these 2 come from that. And so our actual trained come from here. We train our policy, and then we simultaneously train a value to approximate the best value. Again, let me say critic. We train a critic to output the best value given a certain state. And in this case, our state is the context before that specific token is generated. This is a lot to keep track of. So I'm going to kind of draw a little diagram, or we're just going to trace everything that happens, right? And so we start with a prompt X, right? Remember, here we already have the 4 models loaded. I'm going to write them in this corner right here. I'll write them in black. We have our policy, which is the king model we're training. We have the value, reward, and reference. Don't ever forget that. We have those 4 at the same time. Now, this X passes through our policy model. I'm going to label it in green. And now with this policy, again, it's the main thing that we're training. And this outputs a Y value, a Y response. So we have this response. I'm going to keep it gray like this one. So we have this response Y now. That's not gray. Whatever, bro. Yeah, press the wrong color. So we have our response. Technical difficulties. We have our response Y now. So our prompt could be like, what's an alligator? Our response could be a crazy monster that eats people. I've used that example before. We obviously know that that is not a good response, but we'll talk about that now. Right, and so we get that response, and we get this X, and we pass it to our, and I'll put this in dark red, our reward model. Right, the reward model takes a given prompt and a Y, and outputs a scalar reward. Now the reward is going to be in R. This outputs a reward. Just like this outputted a Y. Now, we have our response, right? This is basically this. I mean, intuitively, this is this part that's always talked about. So we haven't done anything complicated yet, right? We have a prompt. It follows through. How can I do so that this doesn't draw? Whatever. We have this X, it goes to the policy, which outputs the Y, and then we get the Y and the X, and we pass it through the reward model. Perfect. Now, let's go to the extra bits. This response Y, as we know, is made up of multiple tokens. What we're grading is the full response. And so remember, the value grades each specific step. And so I want you to realize one thing. Since we're passing this full response and the full prompt, this reward is basically only grading the last token. And it's exactly what we think about when we talk about PPO, right? Or when we just talk about reinforcement learning in general, these online methods, these policy gradient methods. We do the whole rollout. And in this case, the rollout is per token. By the time we pass the X and the Y, we have a reward. But that's only for the last, that's only for this last Y. For YT, let's say. We have a reward for YT. But now what about YT minus 1, YT minus 2, all the way to Y0? We have to give each token that was generated a specific value to it. That's where our critic model comes in. So just like in PPO, we grade each step. Now, the way that we do this is we kind of split this response into what it truly is, right? It truly ends up being a bunch of little tokens, right? Y0, Y1, all the way to YT. And what we do is we pass all of these into our value model. And so we have this value model. I'm going to make it dark blue. We have this value model, which gives a per token value approximation. As you can see, each input, the inputs are the tokens. And so this outputs, what this outputs is basically a value per token. So we have V0, which is the value of this one, V1, all the way to VT, right? So now, whatever the length of this token array is also the length of this value array, right? And so we have this, again, value array that's outputted. It gives a value per token. And hold on to this thought. This is what we pass into, if you guys remember, the GAE, the generalized advantage estimate. And we use this to calculate and output the advantages. Now, the advantages is also another array of A0, A1, all the way to AT. And so just to make this a little cleaner, what you realize is for each Y token, let's say YI, we pass it through our value model. So it's our critic. This outputs a value for that specific step. Then we pass this through the GAE, and this gives us our advantage for that specific step. And this is what tells us if it was a good step or not. Basically, this tells us if it's better than average or not. Perfect. That's awesome, and that's how we generate our advantages. And so you're still probably wondering the weird part about it, right? All this we know from PPO. This is standard PPO stuff, just kind of redirected to LLMs. But how about where does the KL penalty stuff come in? Where does the actual, where does the reference model come in? Well, this is where it comes in. And so let's put our reference model here. I'm going to make our reference model yellow, dark yellow. Here's our reference model. And so we also pass this X to it. Now, if you remember, we talked about, where is it? Right, we need the actual distributions, not the straight up token outputs. So 1 second. So what we do is we output the log probs given x and the y, right? And then also the log probs of the x given y, or the y given x, sorry, for the policy. So these two output log probs. Now there's the policy log probs and the reference log probs. Remember that the log probabilities of the policy are different because that's the model we end up training. This is from the SFT base. And so what we do with that is we pass it through. Let me make this, I guess, a longer string of longer connection, right? We take the log probs of the policy and the reference, and then we take the reward for the final token, and here we perform the KL penalty. Let me erase this. Don't know why. Shouldn't have boxed it up, but here we calculate the KL penalty. And here what we do is we kind of subtract the reward given the beta and then the KL of the policy probabilities and the reference probabilities. This again takes as input the log probabilities of the reference, the log probabilities of the policy, and the final reward. And what we do is we kind of do like a per token pass through all of that, right? And you're going to realize here we also pass both of the log probs, and we pass our reward at 0 to reward t. So you can imagine we ended up making a reward array here as well of R0, R1, all the way to RT. If you remember, these are basically the inputs of the generalized advantage estimate. So I hope that makes sense there. All of that gives us our advantages. And now with the advantages, we do two things. Remember, we're optimizing for two things, the value and the policy. And so I'm going to outline the policy loss and then the value loss. Now remember here, we basically already did the KL penalty for the reward. So then, if you guys remember, I mean, I'm going to oversimplify here, but this goes out here and this goes out here. Along with the log probabilities, I guess I wouldn't put them as coming from there, but you know, wherever the log probabilities are stored, they also are input to the loss. So imagine these are the two log probabilities. And now, what's the loss of the PPO of the policy? It's the same thing. It's the minimum of the ratio. Remember, the ratio is another, well, ratio, yeah, but it's not from policy and reference, but it's from the previous iteration's policy to the current policy. We don't want the new policy to update too much. So the ratio times the advantage at a specific step. And then we do the clipped ratio, which is the same thing, but here we add the just ratio, but we also have the epsilon range to clip it, and then we multiply it by the advantage. That's our loss. And then for the value, if you guys remember the value loss, it's basically our value minus our return squared. So it's this minus this at each step squared. And that ends up basically being just our advantage squared. But in the code, I'll just write it out as this. And so our goal is minimizing this MSE loss and then this clip loss. So we bring this down and we bring this down. That's basically how this all works. I hope that was easy to kind of follow, or I hope at least you guys have the intuition behind it. From this point forward, we're going to code this up, and it's going to be much more clear how everything works. So I'll see you guys in the code just now. Okay, so welcome back, everyone. And now it's actually time to code this beast. And before we start coding, I made this graphic that basically shows how and what we are building. Yeah, I mean, this is going to be in the thumbnail, probably 100%, and probably any blogs or anything I write about this. But this is basically just a cleaned up version of what we drew out at the beginning of this video. And yeah, let's just go straight into what we are building. So first thing we should do is install these libraries, JAX, Flax, all that. And also update your Flax to 0.12.7, I believe. The problem with that is for some reason my Google Colab doesn't update to the most updated and up-to-date version of Flax. And so nnx.list doesn't exist there. And that caused a bunch of problems for me. But yeah, just make sure that you have the right version. You guys will see it now. And another thing, we're going to use a custom built GPT-2 backbone, transformer backbone. And I'm not exactly going to go over it in this video, how to build it. Flax. Yeah, 0.12.7. Make sure you have that. I'm not going to go over exactly how to build it, but I have another video on this channel where me and Gabriel Lucchesi built GPT-2. And also I'll probably do another updated video on this in the future. So you guys can go to that video. Overall, this is just a normal GPT-2 implementation with multi-headed self-attention and everything. Nothing too fancy, right? And yeah, we're going to test if this outputs what it's supposed to output once everything passes through it. There you go, we're good. That's the batch, sequence length, and the hidden size. And yeah, that's basically what we're going to start with. Now, the first thing we're going to do is we're going to build, let me just kind of separate that from this. So here is RLHF. First thing we're going to do is we're going to build our policy model. So the policy model, we're going to use Flax NNX. The policy model will just be an updated version of our transformer already, but it comes with two things. If you guys remember the actual diagram, I should just have it here all the time, huh? Look, if you guys remember the actual diagram, this policy model outputs a Y given a prompt X, and it also outputs the log probabilities. So we have to make two functions for that. We need autoregressive generation, and we need to just get the log probabilities, right? So first thing we're going to do is we're just going to define our init function, config, and our RNGs, very important. Now, the thing about the transformer that I built is just like the backbone base, right? It doesn't really have an output layer. So we're going to have to define the actual transformer. And then we're going to define the head. In this case, it's going to be a linear head. And it's going to be nnx.linear. As we know, we start with the hidden size. But we want to output to the vocab size. Because what we want to output is the distribution. We want to output a distribution a probability distribution per each token or per each word or token that can be possible given our vocab size. That's just something we initialize. And we're going to do this for each model, right? And just the call, we have self and input IDs. Input IDs is of shape, the batch, and then the sequence length. And so given that, we just want to return the linear head after we pass in the input IDs. And yeah. And as I said, we need two functions. We need the log probs. We need two outputs, the log probs and autoregressive generation for our y. So def log probs of is going to be our first function. And we're just going to get the log probabilities of the input IDs that we get, right? So first thing we're going to do is generate some logits. And so we basically just do the same call function here because that's what it basically outputs, right? Input IDs as our, whoa, there you go. And so again, as I said, this is the size of batch, sequence length, and the vocab size. And what we want is the log probabilities through that. So the way you calculate that is you just jax.nn.log softmax, the specific logits, and we do this around among the last axis. So we get the log probabilities of each token in this axis right here. That's what the -1 is. And so what we do now is we basically take the log probs for that token. So token log probs is equal to jmp.take along axis. And so what we're going to pass through is the log probs. Input IDs, and we do this around the last axis. And then what we do is we squeeze that. And so what this basically does is this transforms into a batch and a sequence length array, or sorry, shape. Next step, that's basically just what we return. Basically just returns the log probs of the actual input IDs, not across the whole thing, but just the actual input IDs. And that's a very simple function. The more difficult function would be the actual autoregressive generation. And so first thing we want to do, we want to pass in a prompt, we want to pass in a random number generator, and then we want to pass in max new tokens. Now, this autoregressive generation will be without KV cache. I could do it with KV cache. I don't fully have it studied as much, so kind of just want to skip by this. Plus, this is a very small model anyways, so not much need and not much care for that. Now, first thing first, I want to basically explain how we're going to make this work. So I want to keep this as jittable as possible, as JAX centric as possible. So a pure for loop that just generates a new token, it could get a little inefficient, and I just want something kind of clean. Now, I had a lot of trouble coming up with a way to do this, and I don't think this is the best solution probably, but this is a solution I kind of came up with and saw. So what we're basically going to do is we're going to create this buffer. Just imagine just empty buffer, but it's going to be of size prompt length, right? The length of the actual prompt plus whatever our max new tokens are. So we basically have a full buffer. Then what we do, just imagine this is just zeros all around. What we do is whatever the length of the prompt is, we just replace that. That didn't do nothing, whatever. we just replace that with the actual tokens that were in the prompt. So now we have the prompt in this buffer that we made, and then we have a bunch of zeros out here. And then what we do is we just auto-regressively generate as a while loop until this buffer is complete, or until whatever we consider a mask or our end of sentence token is reached. We basically replace each thing here with our new token. So let's say T, whatever, A, or like take, you know, something like that. The way this looks like in code is basically using jax.lax.while loop. Now what this takes is a conditional function. Our condition function, basically what tells us when to stop. It takes a body function that we've worked with before. And then what it takes is our initial carry. And then what I wanted to output is, well, our final carry, I guess. Oops. And in this final carry will be the buffer. So I'll explain that now. So first thing we want to do is we want to get the actual shape of our prompt. Remember, our prompt is the batch and then the length of the prompt, or the sequence length. Here I'm just going to call it the sequence length. This is equal to prompt.shape. And so as I said, we want to make an array, or a JAX array that is the total size of the prompt length plus the max new tokens. So here I'm going to define a total length that is of prompt length plus max new tokens. So this is whatever prompt length was plus, in this case, 256. And now we just want to create our buffer. The way we create this is we just do jmp.0. We want to do batch and total length. So this basically makes a batch and total length like tensor. And I just want it to be in 32 byte ints, or 32-bit ints. And again, we want to set the beginning part to be just the prompt. The way you do that, since JAX likes immutability, we can't directly edit this new buffer, but what we can do is create a new buffer. And basically what we tell it is that we keep the batch the same, but for the prompt length, from the beginning all the way to prompt length, we set that equal to the prompt. So now if you can imagine just one batch, we have the prompt right here, and then we have a bunch of zeros. And that's what we are, what we're gonna fill up basically throughout this. Now, what's the other thing we need? We need the actual conditional function. So here we have the conditional function, we pass in a carry. We still haven't defined our carry, but what we do know is we need an I, right? We need an I that tells us what iteration we're on. So we grab this from the carry, and basically we just return I less than max new tokens. So if this is basically saying that if I is less than max new tokens, then we just keep on going. Now the other thing we want to do is our body function. We want our carry. And now let's think about what our carry should actually have. Well, we already defined our I, right? But what are we actually updating? We're updating our buffer. And then another thing we have to pass through, so that there could be actual random number generation, we need our RNG to pass. And that's what's in our carry. And so we're going to update this line right here. We don't need these in this carry, but we still have to unpack the tuple in that format. Now, if you guys remember, we have to kind of split our RNG into this specific RNG's, or this specific iteration's RNG. And so here we do that. And this is where we generate our logits. And so we pass, or we get the logits with the input IDs being our buffer at that specific index. And then we calculate our next token with jax.random.categorical, passing RNG sample as the random number generation. And then what we do is logits at the prompt length plus I minus 1 at that specific state. And then remember that this outputs also the vocab size. We don't want that to change. And what we want to do is perform the edit here on axis 1, 0, 1, 2. And now what we do is we create a new buffer. So buffer at this specific point, which is prompt length plus I, we set it equal to our next token. And then what we return is I plus 1. So we say that we're at our next iteration, and we pass the new buffer and the old RNG. And so before we create this final carry, we create our initial carry, which is jp.int320, our buffer, our original buffer, and our RNG. And that just means that what we return here, we don't care about the other things, but we do care about the buffer, and that is what we return. And so in that way, we created basically our generation, our autoregressive generation inside of this buffer function. And this is what we want out of our policy. Now, to be honest, we're generating a fixed number of tokens. There's no end of sentence. There's no padding. There's nothing. So it's very simplified. An actual production setup would have some variable length sequences and attention masks and all that. But for our toy example, this is perfect. Now, we worked on the on the policy. Now we have to work on the value model, right? And so let's create another class. It's our value model, nnx.module. And so remember, we create our initial function, our init, we pass in the transformer config, and we pass in our RNGs. Basically the same thing we've been doing all along. Here we call another transformer, which is the transformer backbone, given config and RNGs. And so now here we want our value head. Now let's think about what we're outputting. What we want is basically a scalar value per token. And so remember that this here outputs batch, sequence length, and the hidden size. But we want this to be, we basically want this to turn into batch, sequence length, and just one, like just a scalar. So the way we do that, or what we do is we create a value head. And that's the same as nnx.linear config hidden size. It's capital, right? Yeah, config hidden size. And then we output to just 1, and we set RNGs equal to RNGs. So then when we call this, we just put in our input IDs, and then we do x equals self.transformer with our input IDs. And then what we do is return self.valuehead x.squeeze minus 1. So since it's batch, sequence length, and 1, we want that one direction, that one dimension just out of here. So we basically turn this into batch and sequence length. So now for each token spot, you are outputting a singular scalar value. That's basically what's going on here. Now we're not doing any additional functions, right? We only need to calculate the value with that. So we're good with that. Pass that through. And then the next model we need is to talk about the reward model. Now the reward model, same thing. We could low-key just copy this right here to not have to type it all out, right? And we want a scalar head here, which is the same thing as this value head. So genuinely just copy it, paste it over. Let's just call it the reward head. And so when you call this actual function, it's a little bit different than the value, right? Because here you want to find the last token. So our job here is to find final token and compute a score for that whole sequence given that final token. And so our return here is going to just be a size batch, right? For each prompt and for each input pair, we just want one singular value, right? We're not doing it per sequence length, we're doing it per batch. Let's pass a mask in. That mask will basically tell us what that final token is. And so same as always, right? We pass it through the transformer, pass input IDs. And then what we want to do is read off of the last real token, right? Now, the way we do that, we just find the last index, and given our mask, right, throughout the last axis, this basically tells us our last index. And so x is equal to x, jmp.arrange x.shape 0. So per batch, right, we just get the last index. And from there, we just self.reward head x.squeeze, squeeze -1, which outputs our batch, just batch. Because here at this point, we just have our batch, but we also have the hidden state of the last token. And let's pass that. And so here we're done with the actual models, right? The reason we're not making a separate class for the reference model, if you remember, the reference model is just a copy of the initial policy model, so there's no need, right? And so now let's follow the step-by-step process, right? Here we're going to split this up again, right? And we're going to work here with the reward model. So if you can label these, right, this is setting up models. So now we're going to talk about how we train the model, the reward model. So this is the second step of the RLHF process. And so if you guys remember earlier in this video, we talked about the Bradley-Terry loss. That's straight up the first thing we're going to do, right? Bradley-Terry loss. So we get the score from the winner, and then we get the score from the loser as inputs. And what we return is, well, I think I talked this part, but we do the minus log of the sigmoid of the score of the winner minus the score of the loser. And so that's a very simple one-liner right there. We just return that. JAX.nn.sigmoid, the score of the winner minus the score of the loser. And we just get the mean since we're doing that across different multiple batches. And so the train step for this would look like this. Here we're playing around with graph defs and states. I've altered a little bit about how I code these parts, especially with the NNX API, but it's still something that I'm frequently battling with. But for now, we're going to explicitly just play around with the graph defs, which are the actual like architecture. So that's like the attention layers, the multi-headed perceptron, linear head, all that. And then the states are the actual weights that are passed through. And so let's start this arm train step, we're going to have a tuple of graph defs, and we're going to pass the state of the model, the state of the optimizer, and then we also want the IDs of the winner, the IDs of the loser, along with the mask for the winner and the mask for the loser. Yeah, and so as with any train step function, first thing we're going to do, well, first let's unpack the graph def of the reward and the, so graph def model and the optimizer. Let's unpack it from the graph defs. As with any train step, we're going to start with the loss function. The loss function passes in the parameters we're actually going to update. And so first thing we're going to do is we're going to merge the model here, right? So nnx.merge, what it does is this split between architecture and weights, it combines them. So here we have the graph def of the model and the state of the model. So now we have a full model. And what we want to do now is we want to create the Y winner. Yeah, pretty much this. So the Y winner and the Y loser. And what we return is the Bradley-Terry loss between the winner and the loser. So here this generates a score for the winner. And again, we want to separate the scores as much as possible. So let's say untrained model gives us a 4 and gives this an 8. For the next iteration, it would give this a 1 and this one a 5, and so on and so forth. That's our loss function right there. So when we do loss and when we do JAX.value and grad, we pass in the loss function and we pass in the state of this model. And this outputs the specific loss value and the grads, the gradients. And now we do the updates in the new optimizer. After we optimizer.update, we take the grads and then the state of the optimizer, and then we have the new state for the model, and we apply updates onto our state model and we just have our updates to that. So what we return from here is our new state model, our new optimizer, and our loss. And so training an epoch isn't too different. We pass the same thing. We pass the graph defs. We pass the state of the model, state of the optimizer, the IDs for the winner, IDs for the loser, mask winner, mask loser. And so we're going to do this using, we're going to create batches, right? So the way we create batches, we're going to do batches of the winners. And I'm sorry, this is multiple, right? Because the train step does it for one step, which is why it's ID winner, ID loser. But here we have multiple, right? So we create ID winners, ID losers, mask winners, mask losers. Those are the batches that we made, right? And so what we want is a jax.lax.scan over a body function that takes in the whatever the initial carry is, and it passes the data of batches. Yeah. And then from there, what we return is whatever we return in the Yeah. Here what we return is the state of our model, so the new state of our model, and then the new state of our optimizer, along with our losses. And that's what we return. So the state of our model, state of our optimizer, we pass that as a tuple, and then we pass the losses. And so here we define our body function, where we have the carry and we have a specific batch. Batch would just be one example. So we could do examples here, call this examples instead of batch. Examples, examples, and here's one example. And so we just unpack everything, right? We unpack that, and then what we do is we do one train step, right? So we get the new state of the optimizer, new state of the model, and then the loss. We do it from train step. And let me call this RM for the reward models train epoch. Train step. And so here we pass everything that we need to pass through here. Graph depth, state model, state optimizer, IDs of the winner. I mean, you see it right there. Mask winner, mask loser. Perfect. And here we just return state model, state optimizer, and our loss. Okay, and then, I mean, this created an init carry for us. All good and well. And yeah, I mean, that's the train epoch for us. Now we have to realize the graph depths don't change. So we have to tell this to JAX. The way we do that is we do rm train epoch. This is outside of the function, right? So this is its own line. Equals jax.jit, but we want to make sure that these are defined as static argument names. And yeah, this is how we train this model, basically. Again, the whole point of this is to lower this amount so that we learn basically what a good score or what a good response to a given prompt is and what a bad response to a given prompt is. And so let's make like a toy data set to kind of visualize this. So number of batches, batch size, sequence length. We're going to create this, right? 8, 8, and 32. And we're going to create this RNG for now. Just give it 42. That's the one I like. So RNG, RNG winner, and RNG loser. Because what we're going to do is we're going to create a fake data set, essentially. So jax.random.split RNG into 3. Yep. And so we're going to create the IDs of the winners to be basically RNG winner, n batches, batch size, sequence length. And let's just say between 180 and 256. So then the IDs of the losers are just something different, right? So we're going to keep this, but let's put another random value, I guess 0 to like 76. And then the mask winners will just be the whole thing, right? We're not going to, yeah, and then we do the same thing for the mask of the losers. Perfect. So from here, let's define a reward model. Kind of let's see how this works, right? We have our reward model. What we pass through is the config, and then the RNGs equals nnx.rngs. Let's give it 0. And we split that. nnx.split reward model. So now we split the architecture from params. And then here we create the optimizer using optax.atom. We're going to use atom. And we're going to create the state of the optimizer. Let's just say state opt rm is equal to rm.init state rm. So here we're creating our optimizer, and then the graph defs are equal to just graph def rm and optimizer rm. This is just something we're creating here. Now, how do we train this? We're going to create a specific number of epochs, let's say 40 or 50, right? 50 epochs. And let's just track the loss, right? Loss history, the win history, and then the loss history, or loser history. And I guess here would be winner. And we do 3 different arrays. And so for epoch in range, number of epochs, for this reward model, what we do is we just basically run that train epoch function from up here. Now this returns the state of the model. So let's say state rm and state opt rm. And it returns the losses from rn train epoch. And then what do we pass in? We pass in the graph defs, state rm, state opt rm, ID of the winners, ID of the losers, mask of the winners, mask of the losers. And so we're going to create our new reward model by merging the new state with the graph def, right? We're going to append the loss history to this. So losses.mean, right? And then what we're going to do is we're going to, for winner history, and by the way, this is .append right here. For the winner's history, we also append what the reward model scored for it. So IDs of winners, just pick 1, mask of winners, 0. And then we just get the mean out of that. And then we basically code up the same thing here for the loser history. We append the score that was given to it there. Perfect. And so from here, we're going to create a couple graphs. So I guess this is going to be a little matplotlib action right here. So we're going to create 2 plots, right? Guilty.subplots. 1, 2, fig size, 2 and 4, whatever. For the first plot, we are going to plot the loss history. Line width equals 2. Let's just do that. And we are going to set the title. This is the loss, right? So we're going to call it the Bradley Terry loss. And then we're going to set the labels as well, right? So the X is going to be our epoch. And then our Y will be where it will be our actual loss. Yeah, that's for the first thing we're doing, the first plot. The second plot we have ax2.plot. There's a reason I was tracking like the scores that we give, the scalar scores that we give per winner and loser. So here we put the winner history, line width equals 2, again, and label is the winner. So title, model score. Yeah, I mean, that's good. Did it for us. And yeah, one last thing we want to print out is basically like the final gap between the winner and the loser. And we just do it from winner history, from the last index of winner history with the last index of the loser's history. I hope these graphs show. We're going to put the first gap as well. First gap of the 0th index, and for each one. Do a tight layout and go to that show. Hope something good is shown. ID winners is not defined. Let's go up. Let's see this. IDs winners. Should be good. ID winners is not defined. Oh, I never even ran this in the first place. ID winners is not defined. Let's see this. So this is inside the actual code. I put ID. It's IDs. It should be good to go now. And let's see our model train, I guess. Again, we're doing fake examples, but as long as the model learns to separate a winner from a loser, we should be good. Okay, something went wrong. Yeah, something went wrong with this. Obviously, nothing is training. Nothing's passing through. So now let's look here. We apply the updates. What did I initialize? Reward model? Initialize. Well. Okay. I see the error here. Here in this loss function, we're passing in params, but here I'm passing in state model. So now when we do all this, there's no gradients passing through what's actually supposed to pass through, right? Here we put params because here we pass in the state model. That should be the reason there was no training whatsoever. Let's see. We should see something, some improvement between separating the fake winners from the fake losers. There you go. And so the first gap was 8, last gap was 12. So it improved on being able to decide a winner from a loser. Obviously, this is a toy model, but still gave us a good example of how this would work, right? So this is the step 2 reward model. Let's just say step 2 that these papers label. 2, yeah. So now from here, from this point forward, we're going to start step 3, which is policy training. Real RLHF. Right. And so the first thing we're going to do is the actual like credit assignments. So this is 2, right? Yeah. Give me 1 second. 3, credit assignments. So what this means is here's where we're going to work with the GAE. with the KL penalty, basically all that. Now, if you guys remember, let's start with the GAE. The GAE, let's compute GAE. You guys remember from the PPO implementation, we have to take in the rewards, we have to take in the values, and then if you guys remember, we have to compute the next value and also pass in a mask. And so the next values, that's another array that we have where we pass in everything from here and then we append the next value, right? So let's say values is 1, 2, 4. What values 1, let me do it up here. Values is equal to 1, 2, 4, right? And we also, let's say next value is 6. So what we do is next values, we append from the first index forward. So we do this, and then we append the next value, which is 6. So then what we have here is equal to 2, 4, 6. It's basically what we do here. And here we compute the TD errors, the deltas. If you remember, it's rewards plus the gamma, a specific gamma, times the next values, times the mask minus values. PPO paper. What? This is weird. Why is it not red? Okay, whatever. Okay. No need to zoom in that much when we have this right here. So this is what we're computing. Our delta is equal to the reward minus the last value. So minus the value, and then plus a gamma times the next values. That's what we compute there. And then if you remember, this whole thing, this whole equation is recursive, or it can be represented recursively. And so literally the same thing that we did last time, we just scan through a body function where we originally pass a 0.0, we pass in the deltas, and we do this in reverse. Now the returns are the advantages plus the values, plus the values, and then what we do return is the advantages and the returns. Now this is what I was talking about earlier, where advantages are equal to the return minus the value. If we rearrange that a little bit, if you think about what the MSC for a value function is, it's this. So this can kind of be represented as advantages squared. So yeah, that's just a little nitpicky thing that I just wanted to show. But yeah, let's create our body function now. This body function contains the last advantage and then the delta. And okay, it computed it for us, but it's the last advantage times the gamma times the lambda. Wait, this isn't what I wanted to do, right? Advantage is equivalent to the last advantage times the gamma times the lambda times a mask, times plus our delta. There you go. Return advantage and advantage. And so let's define our gamma and lambda. Those two are 0.99 and 0.95. Should be working well. Let's review the function. We have our delta. So we have our delta and we add this to gamma times lambda times our final or last advantage. Makes sense. Perfect. And then the other thing is we want to work on the KL penalty. Remember there's a KL or there's a beta. I'm going to put just 0.01. And the way we compute the KL penalty is we take the log probs of our policy, the log probs of our reference, and then we take this beta, and what we just do is return beta times the subtraction between the two policies, policy and reference. And yeah, I mean, that's the credit assignment basically. So in the drawing we had, or let's whip out the picture again, we dealt with, let's edit this if possible. So we got rid of this. We did this part, right? We did the responses. We just did the KO penalty, this part right here. We don't have our reference yet, but we dealt with the reward and we dealt with the GAE. Perfect. So we still have to build the whole pipeline, right? But we've worked with those specific options. And now what we're going to focus on is the actual clipped objective and the actual PPO loss and everything. So I have this code right here that shows why, basically why clipped. Why do we clip the objective? You guys probably have an intuition for this at this point. But basically we have a trust region and we don't want our gradients to overshoot, basically. We don't want the ratio to be too much. This is very similar to this aspect right here, but this is at a model level. We don't want the model's outputs to be very different, and this is at a gradient level. We don't want each PPO step to be so far from what it is, but from the previous iteration. And now let's basically do the two loss functions that we have to worry about. And so we start off with the policy loss function, in which we take an actor, or the actual policy. We take the response. We take the old log probs from before. We take the advantages. And then we take our mask. And so we first compute logits given our actor. And then we do that same thing where we computed the log probs, right? So this is equal to jax.nn.log softmax. I mean, you guys worked with this. I'm going to call this token log probs like we did before. jmp.take along axis, log probs response none, and then along the last, or along the last axis, yeah. And then we're gonna squeeze it. Perfect. So now we want a ratio, right? We want to create the ratio. The ratio is basically just our current log probs minus our old log probs. Now we don't want the gradients to pass through these old log probs. So what we're gonna do is we're gonna pass in jax.lax.stop gradients. Yeah, gradient. And that creates our ratio. So looking at the paper, we basically showed this, right? Looking at our ratio, at our paper, this is the part that we just did. And then we want to do the CPI version, right? So that's just the ratio times stop gradient for the advantages. And then we want the clipped version, which is just jmp.clip. This is literally the same format that we used for the vanilla PPO implementation. It's the same code, essentially. I mean, again, it's the same algorithm, and you're seeing how similar it is, just the philosophical undertaking of viewing this language model as an environment with different states, with our own reward, but it all turns out to be the same exact code. And here we find the minimum, and the loss is just the minimum between the CPI and the clipped version. And what we return is just the loss times the mask divided by the sum of the mask. And then, as we talked about for our loss function, for our value, we take in a critic, we take in a response, the returns, and the mask. We get the values, right, out of the critic. And we calculate a loss. The loss is just the values minus the returns squared, and then we just return the same thing. These are our two losses for our two models that we are training. And so whole thing together looks like, with the rollout and the training, looks like this now. So when we roll out, we want to just collect data, right? We want our policy to generate responses. We want to record the log probs, record the reference log probs. We want to score every token, and then we want to build the per token rewards and run GAE. And then to train, we just update the policy and update the PPO epochs. And so we're gonna create a max new tokens variable, let's say 16, and we're going to put in PPO epochs. We're going to make this equivalent to 4, like we talked about. And now we're going to define our rollout function. So our rollout function is going to take in our graph defs. It's going to take in our policy. It's going to take in our value. It's going to take in our reward. These are the states of these different models. It's going to take in the state of the reference as well. It's going to take in the input IDs. It's going to take in the prompt length and have a random number generator ready. So we are at this step right here. This is what we're drawing out, essentially. We're collecting all this data to then perform the losses on them. But this is what we're building out, right? First thing we're going to do is we're going to unpack everything, and we're going to just deal with the JAX stuff related to the RNGs plus unpacking. And so what that's going to be is, first start with the unpacking. We're going to do graph def for the policy, graph def for the value, for the reward. Technically for the reference, even though it's the same as the policy, I'm just going to keep it through. And then we're going to have two optimizers, right? Because we're training two models, the policy model and the state model and the value model. We're going to still unpack those, but they're not needed for now since we're not actually doing the updates. We're going to unpack that from graph defs. And then we're going to do the random number generation stuff. So here's the model stuff. We're going to create, we're going to establish our models in here. Right? Policy is equal to nnx.merge, graph def policy, and the state of our policy. And do that for each model. Now, first thing we're going to do is we're going to generate a Y. So if you guys remember our autoregressive generate function, it inputs the input, gets the input IDs, and we also need an RNG, right? We're going to use RNG gen, and our max new tokens is going to be equal to max new tokens. We need an RNG gen, so here we're going to unpack this into RNG gen, jax.random.split RNG. If we need more in the future, we'll just add it to this list right here. And so our response is, remember this outputs the buffer, which is batch and total length. We want just the response, which is basically everything that's done after the prompt length. And then here we're going to gather the log probabilities. It's this step right here. These things that they output, that's where we're going to be saving, because that's what we pass into our KO penalty, our GAE, and our policy loss. Very important to have that still around. So we're going to have our log probs for our policy. It's going to be .policy.log probs of response. And then log probs reference is going to be reference.log probs of response. And so, as I said before, our actual mask is just going to be very simple. Like, we're not going to overthink that because that's not very important. It is important, but not for us right now. So we're just going to have max new tokens. We're going to have a mask that is just of this size, gmp.float32. And it's just going to be the whole thing, right? It's just going to be fixed length generation. And now what we do here is where we get the reward. The reward per sequence, and then the value per token, if you guys remember. Let's look at the image again. Outputs a scalar reward for the whole sequence, and this outputs a value for each individual token. And let me, if possible, reset this. Yeah. Where are we at? Yeah. Perfect. So here we just get a scalar reward. We pass in the response and the mask. And our values are given the response as well. And now what we want to calculate is the per token reward. So 0 everywhere except final token. And then we subtract the KO, basically the KO penalty. This is where we add the penalty. So first thing we want to do is we want to find the last index. We do that the same exact way that we did it before. And now we're going to find R of t, right? We're just going to make an array per token, and we're just going to assign that scalar R to the last index of that token. So jmp.zeros like values. So it's just going to be the size of values at jmp.inRange values at shape of 0, last index. And there what we're going to do is set R. And then, so now instead of a scalar, now we have an actual like list with only the reward all the way at the end. And then what we do here is we subtract the KO penalty for our policy, our log probs reference, and beta equals beta. Perfect. And now here we compute the GAE. So what we did here is we basically did this KO penalty step. Now now for the GAE, we're gonna have to take the input. We already have our values array. We have our log probs, and then we have our rewards array. And we pass that into the GAE. So the GAE is, first things first, well, we get the advantages and the returns. And what we do at this point, let's vmap over each batch. we're just going to compute GAE. And what we pass in is the rewards, the values, the next value, and the mask. And so our next value, since this is V mapping, what we're going to do is create zeros of values that shape of size batch, basically. And now one last final step is advantage normalization. This is to keep training stable. So advantages, we're just going to do advantages minus the mean. And we're going to divide it by the advantages, the standard deviation plus this little value, just so that we're not dividing by 0. And now we can return something because now we've collected all the data that we need, right? So we're going to return y, the response, the log probs for the policy, which are the old ones, right? The advantages, the returns, the mask, and the values, or sorry, and the actual reward. Perfect. That's that. And now we just work with the train step and the train epoch. This is, here we did the rollout. Here we collected all the data that we needed. And now we are going to do the losses and then train for a specific amount of PPO epochs. Right, so first we're going to start with train step. Our train step takes our graph defs again, our state of our policy, the state of our value model, the state of our optimizer for our policy, the state of the optimizer for our value. And then it takes the response, the older log probabilities, the advantages, the returns, and the mask. And so, like we did before, we have to unpack this. But since we're not using the reward nor the reference model, we don't have to unpack those, but we do have to unpack the optimizers out of graph defs. And now we define two loss functions, like we did in the past PPO implementation. And so from there, it's just the same updates as always, right? We do a JAX.value in grad and get the losses and the gradients, where we pass in the state. Same thing here. We gather the updates. Same thing here. And then we have our new state after we apply the updates. And what we return is our new state of our policy, the new state of our value, the new optimizer, the new state of our optimizer, the new state of our value optimizer, and then the two losses. And so for our actual losses, what we just do is we return the policy function, the policy loss function that we made before. All we do is merge the graph def of the policy along with the parameters that we passed through. Response, old log probs, advantages, and mask. Same thing here. And yeah, that is one train step. And now for training our batch, or like a batch, right? We pass the same exact things in. The states of our models. Here we pass everything. And this is where we do the rollout and then the training for PPO epochs. So first thing we need is to straight up just unpack everything out of the rollout. This is what our rollout returns. I'm gonna get it. That is equal to rollout. And our rollout takes the graph defs, it takes the states of 4 of the models, the input IDs, prompt length, and RNG. And here, since we pass in an RNG here, we do a rollout, specific rollout RNG, which I'm going to split up here, RNG and RNG rollout. And we can just pass in all of the models and their states through here. That's that. And so for training, here we have our initial carry. In this initial carry, we're going to pack all of the original starting points for the models that we're actually training. And simply what we're going to do is we're going to lax.scan over a body function that goes over the train steps like we always do. So the initial carry, none, and length is going to be equal to PPO epochs. And what's that going to return? Well, that returns the same exact things that we returned up here. So the state policy, the updated version, along with the value model and the optimizers. We also unpack the losses. And so what we return from here, what are we interested in measuring? Well, we're going to pass our updated values, of course, and our losses and everything. Another thing we're going to pass is the mean reward for that specific batch, I guess. And here we're going to define our body function. We already said that we're passing none through in this second spot, so yeah. And so here we unpack again. State of our policy, state of our value, like it said right there. And then we are going to run a train step. We're passing the graph defs, the state of the policy. Basically all this, right? And then what we return is this. Just like updated versions of them. Yeah. And then that's what we return packed together like this. A lot of code. And so in this last step, we do the same exact thing that we did in the previous reward model train epoch, except I call this train batch because the epochs, I just don't want to get confused with the PPO epochs. We JAX.jit it, but we have a few static arg names. And so what those will be the graph defs. Will be the graph defs and also the prompt length. That never changes. Yeah, sorry. Okay. So that's just us doing a bunch of boilerplate, but this is where the actual PPO happens, right? We do the rollout and we train. And then let's just kind of do the whole thing, right? So this is the actual or the full training. Full training. First thing we're going to do, we're going to define the batch, prompt length, the vocab size. All this will be defined in accordance to what we already have. So for example, we have config.vocab size. And then we're going to create an RNG right here. This is like the king of all those keys. And so we're going to define our policy model, RNG's 0 value model. We're just going to use the same reward model that we already trained. Well, trained. We're going to pass in the graph_def RM and the state RM. And then here we're going to make the optimizers, right? So optax.atom states as well. We're going to initialize them to the state of the models. And then what we're going to do here is basically split everything now so we can have our stuff separate the way that we've been coding it up. I've found a lot more efficient ways to go about this now, but yeah, create the graph_defs and yeah, we should be good. Yeah, and so let's make sure the shapes are right for everything. And so let's do like a fake little rollout where we pass in everything that we need to. But let's make this like random, you know, JAX.random .randint for RNG. Like this doesn't matter here. We're not splitting nothing or anything. 1 and vocab size. Prompt length RNG. Yeah, cool, whatever. What we output is this. Turns. And so we're gonna assert a couple things, right? We want to know that the response.shape is equivalent to batch and max new tokens. We also want to make sure that all log probabilities are less than 0. And yeah, I mean, if everything goes well, response is not defined. What do I even return here? Yeah, response. Yeah, equals. These tests should pass. It's no attribute linear. Oh, that's a mistake we made all the way up here. It has no, no, it's because I put linear head. With that update, this should work. It's in log probs of. I guess if I pass all this through. Oh, it's because I defined the model up here. Ah, it was defined under the old thing. Whatever. We'll be good with that. Yeah, now let's okay. So for some reason I put reward here, but this splits from the policy. Or well, I didn't do that. It was the auto complete. But yeah. This is back in the rollout. I forgot what's going on. Oh, I put y underscore shape when it should be y dot shape. Where are we at? Come on. This is why you gotta run these little, too many values to pack. Well, let's see what we return. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right, we're good. All those tests passed. And so now let's just do the full training loop. So again, it's basically the same inputs, right? But here we're just gonna run this for 10 epochs. And we're gonna keep track of the histories, right? Of the policy value and the reward. And then for epoch in range number of epochs, we also want to keep track per epoch. This is just for tracking purposes. And then for input IDs that we have, because we're going to turn this, we're just going to turn this into like data. For input IDs in data, so for each input ID, we're going to create an epoch key. And then basically here we just train the epoch, right? Or train the batch. Yeah. Train the batch. I'm hoping this auto completes for me because, damn, you know? Anyways, yeah. Input IDs, prompt length, and RNG for the epoch. Also, it did that, but I don't know why. And then what we want to do is we want to append the losses. Yeah, but we want to append like the mean losses, right? So yeah, remember here's the mean R. So we have our mean R here. And then here, another float, it's just our P losses, P-loss.mean again. We just want to see the average for this epoch. And another thing, since this is all asynchronous, we're going to have to block our P-loss.block until ready. So yeah. And then once we're out of this loop, of that for loop, we just append this to each list that we made above, and then let's just print something, right? For epoch, epoch plus 1 out of the number of epochs. Our policy would history and for our value, our reward, or in our mean reward would be this. Sure. And then outside of all of this, just making sure I put this in the right loop. Yeah, we just return these three, or all of this. No need for the tuples. Now this should work. So now let's do this for 6 batches or 10 batches or something. Let's create our data key. And then let's just straight up create data. So random.randint, jax.random.fold. Batch, size batch and prompt length with 1 and vocab size for I in range n batches. Yeah. And so let's just basically train this through. We're going to keep this because I want to visualize something. State value. Let's see. State opt p. Data prompt length. Yeah, here we're just passing everything in, and we're going to do this for 15 epochs. And I hope everything works well. We're going to see this train. Okay. Okay, I mean, the mean rewards went up, stabilized at some point around 3.8. That's good. I mean, remember, we're just doing this off dummy data. Let's kind of plot this through though, right? Let's look at these results and see basically what we have. So our loss always stays around this kind of area right here. The value losses and policy losses don't change much, but remember our true signal is our reward. And you can see we started off with negative rewards and we slowly went up. We peaked at 5, at a reward of 5, but then we kind of just stabilized around the 3.7, around there, as you saw in these last few epochs. And yeah, I mean, this is basically how we train these models. I have this visualization code that I made, but called it vhist, but and yeah, I mean, we see that the reward starts going up. The value loss also kind of went up, weirdly enough, but remember our main signal is this reward, and we see that we've successfully trained a policy model to be able to produce high rewards. Now, this is a full implementation of RLHF. There were some simplifications made, like for example, the fixed generation, the random data, no SFT, tiny model, right? But everything we can do here, or everything we did here, we could plug it with actual data and get verifiable results. So I hope you guys enjoyed this video. I know it was a long one, but it's our most complex project yet. And I also now want to take this time to talk about the issues with this. Now, this is a really good method to train and post-train, but just think about all of the pieces that we have, all loosely connected, or not loose, all very connected. If one is a little bit out of sync, the whole thing blows up. We have 4 models that we have in data or in memory, and we're just optimizing for too much all the time. So any pushes to the frontier of reinforcement learning and of post-training a large language model stems from this point forward. How can we make this process a lot more efficient? This is where you start seeing things like DPO, where you saw what DeepSeek did last year with GRPO, and then more modern methods like Dr. GRPO, RLOO, things of that nature. How they are basically different algorithms that approach this same problem from a different lens to try to make this process more efficient. Because again, 4 models is a lot to deal with at the same time. But yeah, that's what we're going to cover in future videos. I hope you guys enjoyed this implementation. This is a really good project to have on your resume. And yeah, hope you guys enjoyed, and I'll see you guys for the next one. Let me finish off with the image that we built. Let's reset this. And yeah, thank you. See y'all next video.